Okay, so we've talked about atomic mass and that it's a combination of the protons and the neutrons in the nucleus. But now we'll get a little bit more in depth with that. And so really, if you think about it on a small scale, protons and neutrons are crazy tiny. And so, I mean, individual atoms then are also still crazy tiny. And so then you start thinking about, well, how would we calculate the mass of a single atom? And they're really too small to measure. And so eventually we'll look at measuring groups of atoms. And if I put a whole bunch of atoms together, well, then maybe I can get something that's actually measurable. But we can also look at isotopes then as looking at their mass relative to a reference isotope. And for example, here we're looking at carbon-12. Carbon-12 is like charcoal, a really stable form of carbon. And it's so stable, in fact, that scientists have assigned carbon-12 a mass of exactly 12 AMUs, atomic mass units. And so there's a little picture here of a carbon nucleus where it's got its 12 protons, it's got its 12 neutral little blue neutrons. And so we say that the overall mass is 12 AMU, really stable particle. Which I guess then, if you take 12 AMU and divide by the fact that there are 12 particles in the nucleus of a carbon atom, then that leaves you with 1 AMU. But now here's what's more important about this. Look at what they're giving me here in this box. Look at the mass of an individual proton, neutron, electron. If we don't talk about these AMUs, these atomic mass units, because whatever they are, they're like crazy tiny. But we understand grams, like a paperclip is a gram. Look at these masses in grams. And what does it even mean? 10 to the negative 24th grams? That's like if I had the number 1.67, and I'm going to move the decimal spot backwards 24 places. Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Yikes, it barely fits. What does that even mean? Like, we do not have an electronic balance that can measure anything that crazy tiny. Nobody does. It's ridiculous. But instead, we can measure large quantities of atoms, and then if we know how many protons are in each atom, and we know how many atoms are in our sample, then eventually we can do some calculations and bring it down to the mass of an individual proton, neutron, or electron. Which, if you remember anything about scientific notation, 10 to the negative 28th is smaller than 10 to the negative 24th. I mean, these are all crazy tiny. But that's why, I mean, electrons are so ridiculously tiny that often we just consider their mass insignificant, so small. I mean, even beyond the proton and neutron, I'd have to flip my decimal spot back 4 more places. That's small. But look at these masses in grams. They're really small, and we really can then say that like the mass of an electron is kind of negligible. A comparison might be like a piano. And so a piano is heavy, and there's lots of keys, and they're all very important to the function of the piano. But if you were to take out one key, the mass of the piano would be about the same. Obviously, it wouldn't function the same, but the mass would be relatively the same. Because again, like one key compared to the size of the overall piano is pretty insignificant. And it's kind of the same in comparison with electrons. Every electron is very important to the function and the properties of the atom, but the mass is kind of insignificant. Interesting. So here, question 14. SEP, Science and Engineering Practice. Developing some models. Each helium atom has 2 protons. Sketch models of helium-3 and helium-4, which have approximate masses of 3 AMU and 4 AMU respectively. Label the different label and differentiate protons, neutrons, and electrons in your model. That's always important when we model, Otherwise, it just looks like a bunch of little dots, and we want to somehow clearly indicate what we mean to be protons, neutrons, and electrons. Okay, so I also have to remember that this number at the end is a way of showing me the mass, the atomic mass, or 3 mu and 4 amu respectively. All right, so let's start these off. A couple options. Helium has 2 protons. So maybe you draw a nucleus and there are 2 protons, and I'm going to indicate the proton by putting a little positive in there. And my other helium would still have 2 positive protons. Those are supposed to be the same size. It's helium. The atomic number, the number of protons, identifies the element. There is no other element on the periodic table with an atomic number of 2 protons, helium. Now, if I go a little further with this, the number of positive protons has to equal the number of negative electrons. And now I don't know if you just want to draw like a little cloud. Here's my electron cloud, and somewhere in the electron cloud there would be 2 negative electrons. Maybe there and maybe there. Maybe you've been told electrons move. Maybe you've been told they're in these rings or shells or whatever. At least I'm putting them in the right location. They're outside of the nucleus. Positive protons equal to negative electrons. But now when I look at the mass, I have to remember that the mass number is a combination of the positive protons plus the neutral neutrons. And we're saying that the mass of an electron is negligible. Okay, so then if I know helium-3 has a mass of 3 amu, there are already 2 protons, then I'm going to put in 1 neutron. And maybe I just won't put a charge in it. So my nucleus should add up to 3 amu. And that's a combination of the 2 protons, and there must be 1 neutron. But then helium-4 has to have a mass of 4 amus. There's already 2 protons in the nucleus, so I'm going to give it 2 neutral neutrons. Mass of the nucleus is 4 amus. Now, when you model, like this would be an option. Maybe I would even go further, and I would put like a little key, where I'd say like the circle with a plus sign equals a proton. Maybe I could do this, like boop, equals proton. Ooh, this is a good model. Maybe this equals electron. And this with no charge is my neutron. Sometimes people indicate protons, neutrons, electrons with different colors. And then they just put a little key down at the bottom. The red particles are protons, the blue are the electrons, and so forth. And that's great too. Awesome. Okay, so I like this. We're able to kind of figure out the composition of the nucleus by using the atomic number and the atomic mass. And these would be called isotopes then. Same element, they're both helium. One just has an extra proton, just makes the mass a little bigger. Okay, but now here's what's kind of interesting, is that when we study atoms of a particular element, we look for 2 things. Number 1, we want to look for what isotopes exist. So if I'm studying bromine, I want to know like what masses of bromine are out there in nature. And so maybe we find that there are 2 common forms of bromine. There's bromine with a mass. Remember these numbers. These are the mass numbers. Or if we're writing it with this other little notation, like this number on top, the bigger number, boop, that's the atomic mass. So I'm studying bromine, and I find that there are 2 common forms of bromine. There's bromine with a mass of 81 amus, and there's bromine with a mass of 79. So that's the first thing that scientists look for when they study an element. Like, what all isotopes exist? I mean, sometimes there's 2 common isotopes. The chlorine looks like there are 2. There's chlorine mass 37, there's chlorine mass 35. Silicone has 3 stable isotopes. There's a mass 28, a mass 29, and a mass 30. And sometimes isotopes could have 4 or more different versions. And they're all the same element, the same number of protons. It's just a couple extra neutrons changes the mass. Okay, so the second thing that we want to study is the abundance of each isotope in nature. So if I know bromine exists in 2 isotopes, I want to know what percent of all the bromine atoms have a mass of 81, and what percent of the bromine have a mass of 79. And then sometimes we put it in pie graphs or whatever. And so here it looks almost like it's 50-50. Like in nature, it looks like about 50% of the bromine is 81 and 50% of the bromine is mass 79. So maybe I'll put that in here. Like this is maybe about, I'll change that to another color maybe. So this is maybe like kind of 50-50. When I look at the chlorine, it's pretty close to like 25-75. So I mean, this is approximate. I'll say it's like approximate 25% of all the isotopes are chlorine 37, and maybe about 75% of the isotopes are chlorine 35. The silicone's a little different. Most of the silicone is mass 28, and a small fraction of the isotopes are 29 and 30. So those are the 2 things that we want to study in reference to isotopes. What masses exist, and then what's the abundance of each isotope in nature? Now look at this question 15, analyzing this data. Looking at the graphs, how does an element's atomic mass, like the overall atomic mass that we usually report, how does the atomic mass compare to the mass number of each individual isotope, and maybe more importantly, the most abundant isotope? And so you'll see down at the bottom, underneath each, there's a little place that says atomic mass equals 79.904 AMUs. If you look at a periodic table, and we're going to look at this one a ton all year long, this is the periodic table that's on the very last page of your book. Let me see what the page number says. It's like at the very end, like just turn to the back of your book. It's like R50. Here's the periodic table we're going to use all year long. We're going to write all over it. You can use it on tests and quizzes. It's going to be great. And so there's all kinds of information in these boxes on the periodic table. But like if you look at bromine, for example, here's bromine. And so I've got a couple things in the box, and some of it makes sense and some of it doesn't. But you see this little number up in the corner? That's the atomic number, which they're kind of showing me on this key. So yep, the atomic number is 35. And then on the other corner is the atomic mass. And so the mass listed on a periodic table for bromine is 79.904. Weird. So the mass number is always the bigger number in the box, and the mass number always has decimal spots, whereas the atomic number is always smaller, and it's always a whole number. Okay, that's kind of weird. Like, eventually we want to figure out why these mass numbers are like decimals. Why can't we just say it's close to 80? Well, look at this percent abundance. Okay, so in bromine, kind of interesting. The 2 common isotopes are mass 81 and 79, and they both exist at about 50% abundance. So they're equally abundant. Well, when we report these masses on the periodic table, we call them weighted average masses. They're weighted average masses. So they take into consideration the abundance of each isotope and the mass of each isotope. So think about it. If I just say that the bromine isotopes are equally abundant, I could basically just average them. And what do you get? Oh yeah, if I take an average, 50% average, they're equally abundant, of 81 and 79. Check it out. It's darn close to 80. 79.904 is the mass on the periodic table. Now that's not the mass of either isotope. There was no isotope of bromine with a mass of exactly 80, or an exact mass of 79.904 for that matter. It's a weighted average. It's a calculated mass. It's calculated looking at the percent abundance and the individual masses. Oh, interesting. But now, like, look at the second one. Okay, so the most abundant isotope, in this case, because there really wasn't a more abundant isotope with bromine, they were pretty close. But now I can clearly tell that chlorine 35 is more abundant than chlorine 37, which also eventually kind of means that it's more stable. Well, look at that weighted average mass. This is the mass that you'd find on the periodic table for chlorine. 35.453. Oh, interesting. It's not that I just add 37 and 35 and divide by 2. It's not just an average if they're not equally abundant in nature. So we take that into consideration, that if 75% of all the chlorine atoms have the smaller mass, 35, well then the weighted average mass is a lot closer to 35. Now it's a little bit higher to represent the fact that there is a small fraction of particles that are a little bit more massive, but the mass on the periodic table is always going to be closest to the most abundant isotope. Look at here, like with silicone. By far, silicone 28 is the most abundant and the most stable. Well, the average mass that you find on the periodic table is really close to 28. And so we should make note of that. How does an element's atomic mass compare to the mass number of its most abundant isotope? It's really close. The atomic mass is closest to the mass of, oh gosh, the most abundant isotope. It'll always be like that. How fantastic is that? All right, so here's my periodic table. We'll come to that, back to that in a little bit. So this mass that you see on the periodic table is often referred to as the atomic mass, but we should just know that it is a calculated mass. It's a weighted average. So there was no one isotope of chlorine with a mass of 35.45. That was calculated based on the abundance of each isotope. Oh, okay. So let's think about this again. Question 16, using some computational thinking. Copper has two isotopes. There's copper 63 and copper 65. And that's the mass of the individual atom, the individual isotope, based on its like protons and neutrons. But on the periodic table, its mass will be reported as 63.546 AMU. There is no one isotope of copper with a mass of 63.546 AMU. It's a weighted average of those two isotopes. So if we wanted to sketch a pie graph that shows the approximate abundance of each copper isotope, let's think about it. Okay, so yeah, like it's kind of a circle. 35 and 65 and 63. So there's 2 units difference. And then I look at my average mass and it's about 63.5-ish. and they're 2 units different. The mass goes up by about 0.5. Would it be fair to say that we're maybe like 25-75? Like approximately 25% of all the isotopes are the copper 65, and about the rest of the isotopes, maybe 75%, are the copper 63. And here's kind of where I came up with the 75-25. There's 2 units difference between the 63 and 65. 2 numbers difference. And the mass goes up by like 0.5. So if I divide 2 units by 0.5, I get like I could say that there would be 4 units. And the way you can check this is to do the calculation. And so if I said 75% of all the isotopes have a mass of 63 AMUs, and 25%, I'm just estimating, have a mass of about the 65. Here's how we plug it in our calculator, which is what we're going to get into in a second. You take that percentage, but use it as a decimal, and then you're going to multiply it by the mass of that individual isotope. So I'm going to use this as like 0.75. And in my calculator, I'm going to plug in 0.75 times 63. 0.75 times 63. And I get about 47.25. Then I'm going to do kind of the same thing. I'm going to use this as 0.25, and I'm going to multiply by 65. 0.25 times 65. And I get about 16.25. Now we're going to add. Okay, so if I add these numbers together, the 47.25 plus the 16.25, I get 63.5. And look at that. It's close. It's pretty close to the weighted average mass that would appear on the periodic table. Now, the difference between a regular average and a weighted average, if I were just averaging 63 and 65, I'd add them up and divide by 2. The average is 64. But the weighted average takes into consideration the abundance. They're not equally abundant. So that's why we have to multiply the percent abundance times the mass of that individual isotope. So you can kind of guess and check. Take your estimated percentages, multiply them as a decimal, times the mass of each individual isotope, and then you add those fractions. And I could also kind of look at that number, that 63.546, and I could tell right away that it's a lot closer to the 63 than it is 65. So right there I know that copper 63 is a more abundant isotope. Okay, so again, here's kind of an example of how this calculation gets set up. If you want to calculate average atomic mass, it's kind of like, in this example, they're showing like it's kind of like calculating a grade when the grade is based on categories, and the categories count for different percents of your overall grade. Now, we don't have like categories like homework and tests and labs anymore. Can't do that. But like it could be like your grade is 90% summative, 10% formative. And so the grade book just adds up the number of points in each category and then multiplies by the percentage. So if in this case the grade was 20% homework and they had 85 points in the homework category, they would take this weight as 0.20 and we'd multiply by the points in that category, 85, to get this fraction, this weighted score. And then we would do that with all the other categories. So this would be like 50%, 0.5, times 75 points in the test category. So even though there's less points in the test category, it counts for 50% of the grade. And then labs are 30%. 0.30, that's a decimal. That's a decimal. There it is. Times 90. And then all we do is add. Like we just add these all together to get the total. So their overall score is an 81.5. And we do the exact same thing with isotope calculations. So here's an example with magnesium. Magnesium exists as 3 isotopes. There's mass 24, 25, and 26. Okay, so then it gives us the abundance in nature. We would plug this in our calculator as like 0.79 times 24 times the mass. And then we get this fraction, this mass contribution, 19. Then 10%, 10% of the isotopes are mass 25. So we multiply the percent times the mass. And 11% are mass 26. Get out of there. 1 times 26. And then once we got the contribution of mass from each isotope, all we have to do is add to get the total. Okay, so if you look at a periodic table, the mass of magnesium should be pretty close to this. Now, there is no one isotope with a mass of 24.4. It's a weighted average. And again, if it was just an average, if I was going to add 24, 25, 26 and divide by 3, I would just get 25. But it's weighted based on the abundance of the isotopes. And if I look at this and right away see that 79% of the magnesium is magnesium 24, well then I should notice that my weighted average mass is really close to 24. They could kind of spin a question on you and say, hey, the mass of magnesium on the periodic table is 24.4. Which isotope is the most abundant? If they didn't give you those percent abundances, well then right away I could tell you, oh yeah, it's got to be the 24 then, because the weighted mass is really close to 24. Okay, so 17 says to compare, in what ways are final grade calculations and atomic mass calculations similar? And maybe we would say something like, we multiply the percent times, in this case it's either the score or the mass. But they're both weighted averages. Both are weighted averages. Okay, kind of get that, right? So we'll practice this quite a bit so that we get to be masters of weighted atomic masses.